Ladies and gentlemen, we are live. We are live at the ECOC conference, the European Conference on Optical Communications, and now we have the EPIC session. This session in which we are going to travel through the entire value chain and understand what companies can do for each other. So this is a very, very interactive show. I want to ask everyone who is watching this, if you have any questions or if you have any room for cooperation with any of the participants today, please post it in the chat. I really want people to start doing business after these 2 hours of your life. And we're going to start the show. We're going to start the show with a person who requires no introduction, but a very good friend of mine, Mark Lutkowitz from fibeReality, who has something to share with the whole community, his personal vision about the present and future of onboard optics and co-packaged optics. The topic cannot be hotter and the speaker cannot be better. Mark, thank you very much for starting this epic session. The floor and the attention of everyone from Europe to the world is yours.
Well, thank you, Jose. It's always a privilege and an honor. And I was talking earlier before we went live that I'm originally from the Bronx, New York, and I was actually thinking about calling this a different dream, but then I thought better of it. But in terms of why it's a pipe dream, this is the an overall introduction, if you will, of why I'm especially pessimistic about CPO. And I think I want to just focus in on the fourth point, the obsolescence. I really think that's important, and it's if we look at all kinds of things like copper and VCSELs, and I mean they hang around forever. I mean, even M13 multiplexers are still around despite the sonnet revolution. And I think the same thing's going to happen with pluggables. They're still pervasive. They're not going anywhere fast. And so
we are desperate to start seeing your slides, Mark. We really are desperate because I have seen them before.
Did I not share my screen?
Yes. So go to the bottom of the Zoom window and the arrow up there, share screen.
I apologize.
Never apologize to me, Mark. It's such an honor to have you here.
Okay, so let's see.
I've seen the slides before the meeting, and I don't want to raise expectations too high, but I am really desperately looking forward to see some of the comments and some of the visions that Mark is going to share with all of us.
Okay.
For many years, Mark has been developing a blog that is a reference in this industry, and it is great to see the views and the summaries of that in this presentation. Mark, we are almost there. If we go to presentation mode, I think we are ready to rock. The floor and the attention of everyone goes to you.
Okay, so let's talk about the introduction, and that essentially the obsolescence thing. I mean, it's just not happening with pluggables. Just like everything else, things just don't go away that quickly. I did want to spend a lot of attention on this. Let me just give myself a little more room here so I can see the slide. Okay, there we go. This happened at a recent EPIC event that I was speaking at. It had to do with 400G pluggables. If you look at the quote, that was really, I found extraordinary. And unfortunate. I'm willing to give the benefit of the doubt to the person who made this remark, who also repeated it on LinkedIn. But I do think that it's very misleading, and I think that's unfortunate. I mean, I guess at times people say, I have my truth, and somebody else has their truth, but I mean, not that I necessarily buy that, but because I think the truth is the truth. But if we're talking about history here, it should not be bastardized because we need history to guide us along. And just because something happened a long time ago, and there may not necessarily be a number of contemporaries around, to verify things. I just don't think people should take advantage of the past in this way. And I think, I think it was a means of for Kobo to say, hey, look, the past is the future, which I think is just meaningless. If something goes away, then just because it comes back doesn't mean it has any real meaning. And so I think that's important. I mean, there's certainly examples of, I don't know, maybe like OFDM or different types of technologies where it didn't have any application in the past, but it certainly might have in the future or might have in the recent past. So, but once something like onboard optics goes away, it doesn't typically come back. And so I just think this is terribly disingenuous. And I hope this is not a trend. I hope, I mean, we're basically talking about technology and science here. And at least we could agree on history. And I just found this terribly annoying and frustrating. Me as the lowly analyst had to respond to it on LinkedIn. I was eventually backed up by a veteran who was around at the time who could back me up on this, on what actually happened with pluggables. But this is really not necessary. And again, I just hope this does not become a trend. I really don't know what it's all about. Is it about desperation? Is it about the fact that people want to get away with anything? Because I can't tell you how many engineers, how many great engineers in the industry I speak for that can't speak out loud about these things for fear they're going to alienate Microsoft, or for fear they're going to alienate Facebook. And I think enough's enough. But certainly, this historic revisionism, and I guess the point that was made was, well, history is, long, and maybe we can get away with this, but this is not the way to go. And I can't remember a time in my 38 years when somebody made a claim like that, and I think that needs to be ended sooner rather than later. So if we look at what COBO's or what CPO is all about, I mean, it's a basic problem where you're trying to match two disparate technologies together. And whether you're talking about technology or whether you're talking about services, like with the phone companies in the past, even to this day, there are remnants where the voice and the data guys don't get together. It was a real problem to get silicon and light together. Packet and optical was always a problem. And now we're trying to get ASICs and lasers, and that's just problematic. I don't think it's necessary. I think it's way too complicated, and this slide just represents one of the reasons why. I mean, you have two disparate elements here, ASICs and lasers, and you're trying to match them up together, if you will. So, and just with the economics, I mean, we're still with a pay-as-you-go model, for the most part. You have these enormous, upfront costs, and with no benefits afterwards. I mean, you're just throwing that out with the pluggables, and I think you're throwing away a lot at a time when. I mean, basically 400G is just kind of taking off, and there's still a heck of a lot of 100G CWDM4s that are being supplied. We're just about to really get heavily into, I'm talking about the hyperscalers now, into 200G. So, I mean, we have a ways to go, and we need to take advantage of the maturity of this technology. And that's the way to do it, incremental, evolutionary. And I just believe that pluggables are going to remain viable, and that's why we'll continue to stay with it. So yes, I mean, not all web scales, fully populate the switches. I mean, that's true. And if we go right to the last point, I mean, these 400 ASICs, people talk about going into the 25 terabit, the 50 terabit. They're actually going into the 12 terabit switches. So this is a very slow process, again, the need for this thing is just elusive. The need for something so complex, when we've proven time and time again with incremental change, with evolutionary change, and that it's just a lot better than trying to pull off this very complex thing that I would say has relatively little support in the industry when it's all said and done. In particular, the stress is on the power. And Jose, I haven't been keeping track of my time, so give me a heads up if I'm going along. It's not necessarily about the cost, but the power savings. But it doesn't seem to make sense to me, because the ASIC suppliers, it's in their interest to go with the highest power possible, basically. Whether you're talking about even with the XSR, you have very little power savings there. And then if we look at the bottom of the slide, heck, I don't know when we're even going to get to 100 G SerDes. I mean, that could be a few years, maybe 5 or 6 years. I mean, I don't know. And then 200 G SerDes. But I mean, it's just no way, in my opinion, if we're looking at a 100 terabit switch, and then you combine that with the next generation 200 SerDes, with the optics in the package, I mean, I guess you keep the optics separate, which kind of reminds me a little bit of silicon photonics in a way, but it's just impossible to cool and power that properly. And so this power thing, I just don't see as very practical. But then after that, when we get to 800G, which certainly is not around the corner, but is a concern of Microsoft, if miracles were able to pull off this co-packaged optics thing, then you also have to add in all these other things, according to Microsoft, in order to make it effective at 800G on power. You need ASICs that are not too cold or not too hot, if you will. They have to be just right. You need 5 nanometer silicon or better. So you need all these other things after you pulled off that miracle of CPO. So it's not as if it stands on its own. And different assortment of CPO issues. And by the way, there's been work maybe going on 10 years, like with IBM and maybe a portion of the government, the Department of Defense. I mean, it's not as if there hasn't been work done on co-packaged optics in the past. I think IBM needed the government to get involved, the U.S. government, because it was just so darn expensive. But some of these things, especially in the beginning, were things that I was looking at, where I kind of had a blog article where I had CPO on trial. But operating at scale, I mean, that's really, that's really an issue. If you cannot get that integration that's needed for all these tech and fab processes, both on the transmitter and receiver side, then you have to get sufficient yields, on the current kludge or RATNest situation that you have. But certainly, the biggest worry is failure to replace it for sure. But some of the other things that I've looked at in the past, the order of assembly. Do you do the ASICs first? Do you do the optics first? What happens if there's a gaffe? I mean, you don't. What happens if you need to rework the substrate that's not yielding?
Mark, we are running a bit out of the time, so could you?
How am I doing on time?
We not very well. So we have 1 minute left.
Oh, I thought you said I had 12 minutes.
Yes. Time flies when you're having fun.
Oh, sorry. Well, I'll go as fast as I can. So basically, the pluggables should be in play for the next 2 generations. And there's no doubt in my mind. 204.8 is so far out as to be irrelevant. There has been backup by, from both Cisco and Arista executives. We're starting to see some talk about divergence. Facebook's not exactly wanting to go in the Microsoft direction. The RFIs was not done in a joint way, and there was some difference in terms of the requirements. So essentially, and then you have these 3 RFIs, including dispersion. So you probably have an ASIC, optic, and ODMs, and how do you reconcile all of that? And the silicon photonics capability is critical. The good news is that if you don't have silicon photonics capability, you may not have to worry about it too much. But I guess we'll have to see about that. Very quickly, it's Google and Amazon who are the most quiet about technology. They're the movers and shakers. It's not Microsoft and Facebook. Okay. And that really needs to be taken into consideration. The 3 C's is very quick. This I'm saying it's going to be the third strike. It's going to be, essentially it's going to be the third strike for Microsoft. And very quickly on the colors project. They could have looked at the previous 10G, what was done on the IMDDZR. They should have followed that, and they did not. They went to something much more complex. They spent a lot of money on it, and fortunately, it was, in comparison to CPO and Kobo, it was not the suppliers that had to put in the money. We do expect Kobo to eventually evolve to CPO, but essentially it makes no sense. That doesn't mean I am sure it'll still happen, but it makes no sense, and this slide indicates that. Again, the Microsoft track record is just abysmal. They don't listen. They don't want to listen. The few people that are in charge of these big projects, they have a shocking lack of advanced network requirement knowledge, and it's just really unfortunate. And again, this OIF CPO thing, it's just going to be one of many. Keeping people in work until retirement and that sort of thing. And anyone who needs a refresher on the benefits of pluggables, which may be the case, it's here as well. So essentially, I'm saying that CPO is not going to be realized like Kobo, and I made a point of saying intradata center because I'm hearing that it might be used for like long haul and things like that. So,
thank you very much, Mark, for a great presentation. It is really tough to condense so much knowledge and so many opinions on the 12 minutes plus a couple of extra, but you managed to convey a very good point. Let me just ask you quickly. So the presentation had, of course, a pessimistic tone, and you said that in the introduction. Let me ask you first if there is some light at the end of the tunnel, because the rest of the supply chain, you're going to see, they are looking forward to know what to provide to companies like you mentioned constantly, Microsoft or Inphi. What is the kind of solution that you see for the volume production of not pluggable transceivers or data center interconnects?
Well, I think we have a long way to go. As I pointed out, we're still doing an awful lot of 100 gig. We're still about to really engage. If you're talking about hyperscale centers in 200G, we're barreling into 400G pluggables. We have a long way to go in terms of anything that's really different, I would say. that'll be needed by the supply chain. And in a way, that's unfortunate because the hyperscalers have really, I would say, been instrumental, and not that I like to blame the customers, but they played an instrumental role in destroying the ecosystem by getting prices down so low.
Thank you very much, Mark. We have the entire supply chain represented with the rest of the meeting. Look at their faces, how excited they are about their presentations. It's going to be a great meeting. And Mark, thank you very much for getting the ball rolling. That was our introduction. So we have some knowledge of where the industry is going. Perhaps, according to Mark, it's not going in the right direction, but it's going into a direction. We need to make sure that we supply all the different tools for that. And we're going to go from integrated photonics packaging, micro optics, manufacturing of indium phosphide, all the way to actually putting big cells in metropolitan area networks and data centers. It's going to be a great session. Let's start. And let's start with one phenomenon. The packaging of photonic integrated circuits started with the pilot production of customized packages following standardized designs. And that story actually attracted so much interest in the world. Padraic Morrissey is here to tell us about how PIXAPP can offer packaging of photonic integrated circuits for any company from pilot to volume production. Padraic, thank you very much for being with us this morning. The floor and the attention of everyone from Europe to the world is yours.
Perfect. Thanks, Jose. Can you hear me and see my screen?
Loud and clear.
Perfect,
Yes.
that's great. So good morning. So yes, my name is Padraic Morrissey. And my talk today is on photonic integrated circuit packaging through PIXAPP. So the real question I want to ask today is really preempting the questions Jose often asks at these meetings. So it's really, what can PIXAPP do for EPIC members and the integrated photonics community at large? And that's what I really want to address in my presentation today. And I really think there's two ways we can help SMEs, startups, and large organizations. And this is really to create standardized, scalable packaging solutions. So again, individual packaging processes that can be scaled to large volumes. And we can also offer generic packaging solutions. And I'm going to actually show how these can be applied for early stage production a little bit later in my talk. So again, first of all, for those that aren't familiar about PIXAPP, I'll give a very brief overview before I move on to really answering that first question. So PIXAPP is the world's first open access PIC assembly and packaging pilot line. So we're a distributed network of some of Europe's leading research and industry organizations that really covers the full supply chain of photonic packaging and related technologies. And we've got partners all over Europe. So we're managed and directed from the PIXAPP Gateway, which is in the south of Ireland. And our director is Dr. Peter O'Brien, that I'm sure most of you have known or have met before. And PIXAPP really has three objectives. So number one, we have to be a single point of contact for PIC packaging across Europe. So it's really one office, one email address, one phone that you can pick up and you can ring, and you can get access to a wide variety of some of the world's best state-of-the-art packaging technologies and related technologies. As well as this, we want to offer generic solutions for the packaging of photonic integrated circuits. So again, right now, one of the things we even find at Tyndall is that the cost of photonic packaging is very high. And one of the main reasons for this is that you're essentially making a customized packaging solution for every SME, every startup company that wants to package their PICs from an MPW or from a dedicated run from a foundry across Europe. So what we want to work on is really how we can create standardized packaging solutions for that early stage prototyping, for pilot level production, that an SME can design their PIC to match that generic package, and then they can get access to very low cost packaging with quick turnaround times and a very scalable approach. And that leads me on to our third objective, and that's to create a credible strategy for future full-scale PIC manufacturing. So right now, if you're an SME or a startup, you can come to PIXAPP and you can get the first 100,000, 10,000 packages created through our pilot line. But again, you need to be able to show investors that there's actually a route towards making 1 million units in the next year or 10 million over the next 5 to 10 years. And that's something we want to establish within PIXAPP as well. So not necessarily to do those volumes right now, but show that we actually have really mature processes that can scale to these larger volumes in the future. So how do we create this route to manufacturing? Well, essentially, we bring together some of Europe's leading experts in the field of packaging and related technologies, and we try to cover the entire supply chain. So we bring together companies involved in standardization, companies involved in the design of actual PICs. So again, these are companies like Synopsys, so we can get packaging design rules really integrated into the software that's used to design photonic integrated circuits. We work with foundry partners, so we work with Leti, IMEC, 35 Labs, Smart Photonics, TUE. So again, companies where before people are actually getting their chips, we want to work with these foundries, these companies, to actually make sure our packaging design rules can really be really established very early on. The people who take part in MPWs or who take part in dedicated runs can actually have our design rules in place from a very early on stage, so they can get access to really low cost and quick turnaround packaging. We work with technology partners. So again, these will be partners that are bringing in specific components, specific parts that can fit into photonic packages. So an example of this would be SUSE Micro-Optics. So I know Wilfred, so SUSE are a partner within PIXAPP, and Wilfred Noel, I'll talk a little bit later, that I'm sure will be very interesting. But we work with SUSE within PIXAPP to really try to standardize how we integrate micro-optics within a photonic package, and how to show that can be made scalable and applied for as many users as possible. As well as this, we work with assembly partners. So again, we've got 4 assembly partners in PIXAPP that can really do pilot level production. So these are Fix, Technobiz, Argotech, and Cordon. And these are the really companies that do the heavy lifting in terms of making prototypes. So these take our standard designs, our standard processes, and can then scale this up to much larger volumes. So it can be making 5 packages, 10, 100, 1,000, really whatever that customer requires in terms of pilot level production. And long term, what PIXAPP is trying to do is really help standardize and mature packaging technology, so that those companies can potentially do millions of units depending on the particular application eventually. But it's really to really give confidence to the market that technology and that supply chain is there in Europe. Lastly, we work with equipment companies, and then this is really important. So as we start to look in the next couple of years to offering and going beyond pilot level production, we really need to make sure that the packaging tools that we actually use to do fiber attached edge couplers or grating couplers are really as optimized as possible. So that's really reducing the cycle time for attaching fiber arrays to PICs, for this grating edge coupling, how we integrate microLens into PICs, really making sure the vision alignment system, the high-speed pick and place tools are really as optimized as possible to really make packaging more accessible, faster, and ultimately more cost-effective, I think, for everyone. So then back to my original question. So what can PIXAPP do for EPIC members or other members of the integrated photonics community right now? And there's really 2 specific areas that I'd like to focus on the remainder of my talk. So number 1, I think we can offer validated and scalable packaging assembly process and technologies. And 2, we're now starting to offer actually generic packaging solutions for prototype production. So I'm going to start off with talking about our validated and scalable packaging processes. So one of our main goals within PIXAPP is to really offer customized packaging solutions through standardized packaging technologies. And that's I suppose what we're trying to do there is that it's very difficult to set a complete standard for how people are going to want to package their PICs, whether it's what an SME, what a startup would want, maybe very different to what a large company wants. So it's very difficult to set one global standard for something as diverse as packaging. So instead, what we've tried to do is really look at a photonic package and really pick out the core processes that go into the majority of photonic packages and standardize each individual process. Then a customer can come to PIXAPP and they can essentially build their own custom package by combining these really validated and scalable packaging building blocks together in their own unique way. So essentially it's customization through standardization. It's maybe a little bit of a conflict there, but it seems to work quite well for us right now. So what are the types of processes that we're actually trying to standardize? Well, there's some basic processes and then some more advanced processes that can add functionality to PIC packaging. So again, some of the basic ones would be things like edge coupling and grating coupling to PIC. So again, one of the more common processes in any type of photonic package is how you attach a fiber array to the device. So what we've been doing in PIXAPP over the last 12 to 18 months is really establishing really best-in-class fiber array attach processes of fiber arrays to edge couplers, to grating couplers, using laser welding and similar technologies like that, investigating how we do micro-optic integration, photonic wire bonds, PIC-to-PIC coupling, etc. Electrically, it's looking at even things like DC ribbon wedge bonds. So again, it's really standardizing the metallizations that are used on silicon nitride, indium phosphide chips to get the most reliable, the most repeatable, really the most standardized way of actually interfacing your PIC to the outside world. As well as this, it's really really working towards DC and RF interfacing as well. So again, a big challenge for us right now is how you get RF signals to and from a package. So again, if you're going 40, 50 gigahertz, how you get those RF signals is very complex, and it really adds quite a lot to the cost of packaging. So we're trying to really create standard interfaces and how you can actually do pilot level production of photonic devices using really a standardized process as possible. As well as this is looking at flip chip bonding. So again, single die level, die to die bonding. So integrating drivers onto PICs, and also looking at more large scale processes that we can increase capacity. So doing laser assisted reflow and very high speed pick and place tools for wafer scale assembly of electrical ICs onto PICs. In terms of terminal mechanics, it's looking at tech integration, thermistor integration, how can design customized heat spreaders to really manage and optimize the heat flow in packages. And then lastly, it's looking at free space sensing. So again, quite a large area of interest for us right now is microfluidic integration. Again, this is particularly important with COVID-19 and antibody detection. So again, we've got a suite of packaging building blocks that are designed for silicon nitride PICs. And again, it really covers how you actually get silicon nitride PICs into microfluidic cartridges to ultimately do very low cost biosensing with pluggable optical connections. So it's combining really epoxy gluing processes for gluing PICs within cartridges, and then using micro optics to actually create pluggable connections to and from chips. So you can do very quick optical biosensing of samples. Again, we're at the stage now in PIXAPP where we essentially have a menu of packaging processes. And this has really been kind of what's driving us over the last probably 6 to 12 months. It's creating essentially this menu of packaging processes. And I'm showing a snapshot of this here. So essentially what we have now is really this menu. So when a customer comes and talks to us in PIXAPP in our gateway, whether you're an SME, a startup or a large company, you essentially have a list of packaging processes that we've already validated. And we validated them on silicon nitride reference PICs, indium phosphide reference PICs, and silicon reference PICs. And essentially we now have a really good understanding of the process. We know how much it costs, we know how scalable it is, and we know the expected coupling efficiency. So again, that customer who engages with us can come and literally pick and choose from these building blocks and build their own customized packaging solution. And we can discuss cost points, how scalable it is, what partners you need to work with. Can you just deal with one of our packaging partners, or do you need multiple to really get the volumes you require? So within PIXAPP, what we've done to demonstrate how these processes actually work, we're currently in the process of making 4 technology demonstrators. And these show how these building blocks can actually be combined in some very unique ways to do advanced packaging. So again, no one may use all these processes in these ways, but it really just shows users that, okay, these building blocks are there, they work, and they're actually scalable. So on the left, it's kind of probably one of our most impressive demonstrators visually. It's our Datacom demonstrator for, I think it's 200D data communication link. So again, it's using a silicon PIC from IMEC. Again, you can see the chip being rotated on the bottom left. So on this chip, we've a scalable process for integrating micro lenses, hybrid integration of a 3.5 laser directly integrated atop the silicon PIC. And we also have drivers and an amplifier integrated there as well. This PIC can then go into the larger package where we've a standardized RF PCB board for evaluation and test. And we've also got an optical connection. So using micro optics to create a pluggable optical connection between an MTP or an MPO connector and the actual chip itself. On the right-hand side, we've got a very different technology, and this is where we're combining maybe some of the same building blocks in a slightly different way. This is where we're looking at microfluidic integration. So again, we've developed this PIXAPP biosensor reader, and it's essentially a system that you can plug in a microfluidic cartridge and get free space optical coupling from an optical fiber array to a silicon nitride PIC. And again, in this image here, you can actually see it's not working as well as I would like, but again, we're actually have a video of showing a microfluidic sample actually being interfaced over silicon nitride PIC using one of our special gluing process for actually connecting a PIC within a microfluidic cartridge. So the type of building blocks we would have here would be very stable gluing processes that don't impact biofunctionalization, as well as processes for integrating micro lenses onto PICs as well. And this is really key to us establishing pluggable optical connectivity between PIC and the outside world without the need for active alignment every time. So again, let's move on to the second way I think we can help EPIC members and really everyone in the photonic community in Europe right now is really to offer generic packaging solutions for prototype production. And this is something we've really been pushing and working very hard with EPIC on in the last couple of months. So again, it's really creating packaging, essentially 2 different types of products, essentially, or what can be considered products. So essentially we have what's called our PIXAPP GCP10 fully off-the-shelf photonic packaging solution. So essentially what this means is that if someone designs their silicon PIC that uses grating couplers with our packaging design rules in mind, well, there's a fully off-the-shelf packaging solution available for them to use. So again, it uses standard PCB, standard base plate, standard fiber arrays, and again, it's a really low-cost, low turnaround time photonic package. For customers that have kind of more larger requirements in terms of number of channels, electrically or optically, there's again a different standardized design that's not as off the shelf. It can handle a customized PCB. So again, it's there's an additional NRE cost in designing your own PCB. But what's critical here is that the fiber attach process in both of these packages is fully standardized. So again, this is something that helps drive the cost way down. So again, you're changing what happens on the PCB board for this early stage prototype production, but you're not changing the actual packaging process. The wire bonding is the same, the fiber attach process is the same. So again, that really makes the packaging cost really go way down.
Padraic, we need to hurry up a little bit,
Oh,
but I
sure.
think we are by the end already.
Yeah, two slides left. So again, these packages are already out in the wild. Again, here's a snapshot from a press release from one of our partners, Fix, that are actually using these packages already. So again, they're making these packages for customers, advertising their websites. Again, we're seeing quite a lot of demand for them already. And my last slide is just really just to show where this is going in the future. So again, we're not just stopping there, and we're now working on an edge coupler equivalent package. So again, a small package that's designed for low-cost prototyping. Again, it's standardized PCBs, standardized process for edge coupling. And long-term, what we're quite excited about is this package here. So it's going to be for prototyping RF packages. So if someone is working on a transceiver package using indium phosphide chips from foundries in Europe, well, we want to actually develop a really low-cost gold box solution with high-speed evaluation boards for really quick turnaround time of prototype packages. So again, this is something we're working on in the next couple of months. But I think it would be a very efficient way of actually coupling or of developing packaging prototypes.
Thank you very much, Padraic, for a great presentation. We have some questions in the chat. The first one is coming from Giorgio Grasso. He's asking, do you have reliability data on your packages?
Yes, so that's something we've been working on quite a lot in the last couple of months, actually. Slowed down by COVID, but we've done, or by COVID-19, but we've done reliability testing on the fiber array attach using different epoxies. Our hybrid integration lasers are undergoing reliability tests, hermetic sealing tests. So that's something we're very keen to work on. So it's a long process, but something we are working on.
The second question comes from Barbara Vesgenova. She's wondering, what is the alignment resolution you can achieve for attaching optical fibers?
Yeah, it's a tricky question to give a one straight answer for, but again, with the alignment machines that we have at our partners, I mean, it's sub-micron alignment tolerance, but I think the real question then is how that shifts after epoxy cure. So we can do sub-micron alignment of fibers, but it's how these shift after curing is, that can move by a micron, 2 microns. That's where a lot of research has to go into standardizing processes. But
the next question comes from Effect Photonics, one of the success stories of the European ecosystem. Aaron Alvarez, he's wondering, does PIXAPP design interposers for the chiplet packaging, or does PIXAPP serve as an intermediary to third parties?
Essentially, we act as that intermediary. So we've got some partners within PIXAPP that can design electrical interposers like VTT. So again, we would work with a company like VTT to help a customer develop their own electrical interposer. And we're also developing standard interposers that you can actually use as well. So again, it's a little bit of both. We do our own design and for standardization, but we can also act as that link to other partners that can do silicon nitride interposers for motor pitch reduction, as well as electrical interposers on LTCCs. For
3 years plus, you've been offering this technology to different market segments, not only in the datacom telecom, but also in the LiDAR, in the medical industry. What kind of requests would you highlight that you are receiving from the companies who want to put new products in these markets?
Yeah, so some of them we can't really talk about, they're confidential, but in general, what we're seeing is even in micro optics in the medical sector, it's been very interesting. They're looking for very simple processes that are extremely reliable. So again, it's integrating micro optics lenses on fiber arrays for something like catheters. But it's really investigating the epoxy. So they're really concerned with having the best type of epoxy, the most robust process, and things like that. Quantum is also a very exciting area. We're getting quite a lot of questions related to quantum and quantum applications.
Every photon counts. I love quantum technologies and integrated photonics. Padraic, thank you very much for being with us. Stay tuned because there will be more questions coming your way. And congratulations. Congratulations on what you are achieving already in this industry. It's really a paradigm shift. And we go from one success story of the European ecosystem to another one. We go to the manufacturing of indium phosphide photonic integrated circuits in pilot production. JePPIX pilot line is setting up production for integrated photonics in an industrial manner. Thank you, Kevin, for being with us today. Tell us what you are achieving, what you are assembling, and how the other companies can help you. The floor and the attention of everyone from Europe to the world goes to Eindhoven, goes to Kevin Williams. The floor is yours.
Thank you very much. I need to get my screen share going.
Yes.
I'm hoping that worked.
Perfectly.
So thank you. I will be presenting the JePPIX Photonic Integrated Circuit Manufacturing Platform. Many of you will be aware that JePPIX has focused on making photonic IC technology accessible to many new markets. Over the last couple of years, we've put a huge amount of effort into making this technology into a manufacturing platform. And I'd like to share with you what we've achieved so far and what the new opportunities are going to be. Switch screen. So, indium phosphide integrated photonics, sometimes, not often, but sometimes confused with silicon photonics. But I'd like to clarify exactly why indium phosphide matters, we have the lasers on board. We have native amplifiers. We have native high-performance MQW modulators. We get the cost down for the photonic circuit as a whole. The size, the weight, the power, it all comes down. The energy efficiency, very powerful in the integrated photonics indium phosphide platform. And with the platform we're building, you can customize your light sources. You can build wideband tunable lasers. You can get your density right down for very high performance, high functionality circuits. And because this is an open platform, the designer drives the circuit functionality. We have the essential building blocks inside the chip. So some of the concerns we hear from other platforms, the reliable integration of lasers, for example, that's dealt with. That's embedded within the chip itself. We don't have to worry about those tricky passivations. Hermeticity problems can be solved in different ways. So a lot of the challenges that we face in circuit building are transferred to the design phase. We have lasers inside, we have amplifiers, detectors, modulators. That's here, that's now. And also, of course, we have the passive waveguides, the tight bends, and polarization functionality is coming on stream shortly. So we see this as a no compromise platform. It's open, it's configurable. We've got the best in class components for many exciting circuit applications. And our focus for the last couple of years has really been to move from the MPW approach that you see on the left. This wafer here shows many designs from many application spaces. And now we're trying to ramp this up. And this means a lot of things. It means getting much more robust design capabilities, much more representative design models, a better visibility on what the manufacturing process delivers at the circuit level, and also building up the test infrastructure around it. So in TRL levels, we're transitioning now from our first prototypes at TRL4, and we're getting up to TRL7 for many different products. Of course, this has been done already for long-haul communications, for the internet transceiver technologies that we see from Lumentum, Finisar, and Infinera, and more. That's for very specific product developments. What we're trying to achieve here is a platform for any product development. It's generic in that sense. And to do this, to get from prototype to production, we're focusing on that pilot manufacturing phase, where we learn to do the design, the manufacture, the test at a smaller scale, but using exactly the same processes that you would use in production. And the challenge we have been addressing for the last 2 years, is fully integrating that design flow from the first concept all the way through to testing at scale and producing at scale. And to make this manageable at a commercial scale, we're also introducing the commercial account managers to handle specific workflows. It's a fully industrial supply chain. So we start from the design. We've spent a lot of time accelerating this process. The design tools, many of you know, have been out there in the market for some time. They're very powerful. We have simulation tools, compact models, layout tools. They do the business at the prototyping phase. But when we move up to creating product, we need traceability. We need tolerances to be known up front. We need IP blocks when we want to sort of accelerate our route to market. And we want to be sure that when we're using these process design kits, they're accurate, reproducible, time and time again, whether we design a year ago, whether we design in 3 years' time. So we're putting in place all those processes so that the PDKs are automatically generated, the design manuals are fully traceable, and we can see exactly what the spreads are going to be at the building block level, so that when we build our circuits, we see exactly what the yields are likely to be, where the dropouts are going to be, and we really understand how to optimize our designs. And Throughout the next sequence of slides, I'll name some of the businesses that are proactively engaging in this program at the moment, and you'll see in the chat that many of these businesses are actually online today. Pilot manufacture is at the heart. We have 3 fabs involved, Fraunhofer, Heinrich Hertz, 3.5 Labs, and Smart Photonics. The key point here is that there is no non-recurring engineering cost on the process. These fabs have been in business for some time. They deliver excellent product. That has not changed. What is changing is that we're building a process where you can take that process off the shelf. And we're building up the support around that process so you can design for it, test for it, without changing the process. And that can be very powerful. That can accelerate product development. It accelerates the reproducibility because we get far more businesses using the same process, and the fabs are able to accelerate process centering for the needs of the customers. We're able to gather more data on the building blocks, so the tolerances are known up front. And these values are systematically going down already. We're seeing the CPK values improving. We're seeing the tolerances in the PDKs. They're going to be released in the next release early next year. And the process maturity develops along with that. So we're getting high performance on demand. You don't have to run up a process for your own specific product. You can take this latest state-of-the-art generic process and build your design around that. And test, of course, is the next stage. Every PIC will be different. Every design will address a different challenge, have different metrics for yield, performance. So we're developing together with FiContact. Fraunhofer has been involved as well in some of these methods, and Eindhoven, high throughput testing methods that are configurable at the design phase. Quite often in product development for PICs, the design and test sequence are highly customized and highly tuned to the design itself. And that involves a lot of relearning, and a lot of that know-how is difficult to acquire. So we're developing the methods so that automated tools commercially available can be deployed with the same scripting methods, the same methods we have in design to drive those tests. And that allows us to understand the test outcomes even before we've taped out, hone our testing strategies. So we can incorporate known good die selection within the foundry offer over time. And we've also got evaluation boards coming through. I think in light of the previous presentation, it's very important to emphasize here that we're collaborating quite effectively with PIXAPP as well. The tooling here is jointly developed. We focus more, of course, on the known good die selection, but that's, there's an excellent synergy there. And that's important because that enables businesses to go on to use the packaging capabilities. We also aim at a test as a service capability where PICs could be functionally tested remotely. That will take time, so I'm not going to overpromise on that, but we're aiming at 2022 to have that sort of capability. I've kept this short. I hope Jose appreciates that. The message I'll share really today is that we're launching now. We're getting ready now to accept business at the pilot manufacturing phase. We have information online for you to follow up more. The JePPIX.eu pilot line website will orientate you. You can email us. And we'll be launching a roadmap very, very shortly. JePPIX has always done this, issued roadmaps. 2020 is no different. We're going to issue a roadmap, and you're very welcome to register your interest for that. And that will be available in the coming couple of weeks. I should finally acknowledge that this capability is enabled because the European Commission has been financing the project Impulse, and this allows us really to focus on this transition, this step from indium phosphide capability to commercial manufacturing opportunity. Thanks very much.
Thank you very much, Kevin, for presenting this. It is truly great to have these initiatives going on, funded, as you said, getting the support from the European Commission, but setting up fully industrial, this is not research, fully industrial manufacturing. I love what you said, that you use the same process that the industry will take out to take this to volume production. I want to highlight something that you said. This is not a closed club. You are looking for more cooperations and for companies who can supply extra technologies to the pilot line. Is that correct?
Absolutely. Embedding a photonic IC in a product is not trivial. There are excellent reasons to do it, massive benefits, but it's not easy at all. The packaging is the start of it, but just integrating that in your whole product, that changes your business model quite often. And any business is able to help with that transition are very welcome to engage with us. We're very keen to build these supply chains, these communities that can support the uptake of technology. Because businesses have their own skill sets, and it's going to be very valuable to be able to leverage the capabilities of others.
In the coming presentations, you're going to hear a lot of examples from micro optics to new solutions for the packaging. There's so many things that we can do together. We have a couple of questions in the chat. The first one is coming from Giorgio Grasso. He's asking the $1,000,000 question. Can you comment on the cost competitivity of indium phosphide versus silicon photonics?
Pleasure. I think there are many misconceptions around this. Indium phosphide is a wafer-based technology. It's a semicon technology. It scales exactly the same way. We process wafers, we process batches of wafers. We process as many wafers as the market asks us to. At the moment, indium phosphide is at 3 and 4 inch wafers. That's sufficient capacity to serve the whole PIC market. If you listen to Martin Schell when he defends this, we often hear this. So capacity is available. The cost is defined by the market size, and that's no different for the silicon photonics community. Some of us may have been on the PIXAPP workshop on Sunday, yes, where we heard these arguments from the other side. Well, have we got the products to motivate that cost base? So this comes down to the market size. What can the market support? And in terms of the cost per chip, I mean, they're comparable in many ways. If you look at the MPW pricing, comparable. So it's what the market can support.
All right, the second question comes from Effect Photonics. Is there a reliability DVT program for the devices coming from the pilot line?
Yeah, that's a very interesting question. We've not looked into that at the product level. We're not going to. That is just too diverse. I know Effect will be very much on top of the reliability capabilities required for the communications sector. That requirement will be very different for sensors in extreme environments. But there are many similarities. And when there are similarities, yes, we step in. So we're actively looking at characterizing aging properties, for example, looking at ways of managing infant mortalities, that sort of thing. Yes, that's very much within our scope. But when it comes to reliability as a product in the field, I think our customer base is really going to have to work with us on that one, because the requirements are so diverse.
One of the big paradigm shifts that you are bringing to the industry, it's my personal opinion, is wafer level testing. And when it comes to wafer level testing on indium phosphide, it's not easy to do because you cannot easily couple the light in, but you actually do have lasers and detectors already integrated in the material. What is the approach that you're following? And is there an optoelectronic probe that Phicon would integrate in the machines to do the wafer level testing?
Could I take a step back? Actually, it's a very well-defined field. There is incredible wafer scale testing within some of the big foundries. That is, sort of the vertical integrated foundries like Infinera, Lumentum. The capabilities are phenomenal, and also in the silicon photonics world. And yes, there are methods, and the acceleration you get with some of these automated tools. For some markets, it won't matter whether you test at die or wafer level. But we're doing a number of innovations. We're doing wafer scale testing where we're using PCMs and clever electrical methods for really understanding functional performance, predicting functional performance. And when you get large amounts of data, that becomes quite manageable and very insightful. But we're also focusing quite a bit at the moment on how the customer is going to benefit. And that's really on the automated die level and bar level processing. That's our main focus right now. But both are active areas of study. The wafer scale testing is more in the fabs.
I have in the chat a comment from Gert Appleton asking people to feel free to check out the Smart Photonics virtual booth. I do recommend that you spend some time checking them, and you can see what paradigm shift the JePPIX pilot line is setting up in these production foundries. Thank you very much, Kevin, and congratulations on the great job that you are doing. We started with a broad view. Then we talk about pilot production. Now we want to know how the market looks like, and there is no better person in the EPIC community than Eric Munier from Joule Development to tell us how the market looks like for the companies in the supply chain. Thank you very much, Eric, for being with us today. The floor and the attention of everyone goes to you.
Thank you, Jose. I will share my screen. Can you see it?
Not yet. We go to the bottom of the room, the bottom of the Zoom room, the share screen button with a green arrow up.
Okay.
And there it will indicate which screen to share and will be in business.
Okay.
It is looking sharp. Yes, go to presentation mode.
Yeah. Okay.
The floor is yours.
Okay. Thank you, Jose, for the invitation. So my presentation today will focus on market for photonics. I will cover communication, but also I will introduce what's going on in sensing, and we'll also conclude with what we can do with photon for computing processing. Because as you mentioned, Jose, there's a big trend for quantum computing, and photon-based qubits are very powerful, probably for future computers. So just as a very short introduction of UF development, so you probably know one consulting company working in photonic sensing, but also in semiconductor software, more or less. And all the information I will show today is extracted from 3 main reports. One on silicon photonic, focusing mostly on this technology for datacom, telecom, but also sensing. Another report on optical transceiver is a very complete overview of optical transceiver for datacom and telecom with information on supply chain, market forecast, technological trends. And also another report on quantum technology, where we talk about the this disruptive technology, about the supply chain, challenging technological challenge, what will be the application for quantum technology in the futures. So just about photonics. What is very powerful with photonics is that it's a transfer technology. You can find photon everywhere, from high-end market to high-value application. I mean, from defense aeronautic to industry, automotive, up to telecom and consumer. It means that at one hand, defense aeronautic, you will have high added value product, maybe low volume, 10K a year. On the other hand, for consumer, telecom, datacom, it will be millions of units, lower cost, but at the end, we'll have photon everywhere. And then also, according to the application, photon we will use in different ways. Photon can be used for lighting, imaging, sensing, communicating, computing. What is powerful with photon, you can control them through intensity, phase, wavelength, polarization, coherence, and so on. It means that on one side, you can use photonics as sensor, and it's more on the left side on my graph. You will have sensor in automotive for LiDAR, ADAS, optical sensor in healthcare. On the right side, photon will be used more for datacom, telecom, and the next goal is to use photon for computing, quantum computer, quantum internet, cryptography. I will show later that there are already some nice development, already product involving quantum cryptography in consumer product. But at the end, it was very powerful with photonics. It's both a transfer technology for many kinds of applications, and also because you can play with different parameters of photon, you can use for lighting, imaging, communicating, computing, processing. So there have been many changes over the 20 last year in communication. I remember in the 19, the data rate was a range of 2.5 to 10 gigabit a year. But today, according to what Cisco is saying or the different analysts, the growth in traffic is increasing from 30 to more than 40% a year. That means that we're moving to higher data rate. Metro and local network now are using coherent and DWDM technology to enhance both the distance and the data rate. So today, most of the data rate for metro access or DCI, metro core long haul is at 100 gigabyte, 200, 400 starting to be implemented, and we're heading to 60, 100 gigabyte. We plan that in 2022, 60, 80 gigabyte will start to be deployed in volume. So for Datacom, it's also very important to consider that most of the traffic is inside or enter data center. So it means that we need a lot of different transceivers, and according to the different level in data center, we use different technology. In Intra-rack, for very short distance, we're still using DAC attach, but we are moving to active optical cable for higher data rate. Also, for inter-rack, lift to spin, spin to core, moving for less than 50 meters, 5 to 2 kilometers, 2 kilometers, 10 kilometers, we will use optical transceiver or active optical cable, and we will move to today 40, 100 gigabyte to 400 gigabyte in the futures. Here it is a sweet spot also for silicon photonics. I've been tracking this technology for more than 10 years now, and I'm very excited to see that it's taking the lead in the data center for 100 gigabyte single mode fiber for a reach between 500 meters up to 10 kilometers, 400 gigabyte data rate. So silicon photonics, what are the motivations for this technology? First, you can achieve smaller component. Then it's very efficient technology, very powerful technology when you need to have optics and electronics getting closer to each other. Also, you will have higher data rate, lower power consumption, and because it is bent on wafer scale, you will leverage semiconductor industry. So at the end, you can have better reliability when you move to larger wafer scale from 8-inch to 300 millimeter. The yield is improved, so reliability will be improved. Because it's a batch process, you will lower the cost, and it's very important for some company like Facebook that announced that they want to have very low cost, very low value of US dollar by gigabyte, and silicon photonics is a technology for that. And something which not always mentioned, but if you look at what's like Intel, there are a lot of automation using silicon photonics. For example, assembly testing can be done wafer level. So also by moving to silicon photonics compared to legacy optics, you will have more manufacturing automations. So of course, today silicon photonics is mostly used for datacom telecom, and the first product is 100 gigabit plug transceiver using current and direct detections. And there's been announcement this year for 400 gig transceiver data center and ZDAR current transceiver. The next step, and Intel is very well advanced in that, is to have co-package switch for 25.6 or 51.2 terabyte per second. I've been talking with Intel recently, and I believe they are very close to launch the first prototype to the first demonstrator testing of this co-package approach. But actually, silicon photonics is a technology. You can make a parallel between silicon photonics and CMOS. It's the only difference is that we replace with photon, no longer with electron. So as the technology gets mature and mature, you can use it for other applications beside datacom and telecom. For automotive, for example, for fiber optic gyroscope for photonic, or LiDAR for ADAS or robotaxi. Medical, also there are some company, Generalite in the US, developing immunoassay for photonic point of need using silicon photonic. Also, there's a development for OCT for ophthalmology or other application. Even some company developing sensors such as environmental sensor, gas sensor, INOS are investigating the use of silicon photonics to lower the size and the cost of their chips. So, because technology is getting mature, of course, more and more players are getting interest into the technology. So you can see that similar to the semiconductor industry, a complete silicon photonics supply chain has been set up. Supplier of substrate, SOI wafer, like Soitec, fab, proposing wafer foundry services like TSMC, Silterra, Skywater, electronic component, company involved in electronic component high-speed moving to silicon photonic, specifically company developing switches like Broadcom have high interest in photonics because, as I mentioned, at one time there's converging of electronic and optics for co-packaged switches. Company doing optical transceiver. Also, there have been announcement of Finisar moving to silicon photonics. Of course, there are more and more companies developing silicon photonics. Today, most of the shipments are done by Intel with #1 and Luxtera, which knows Cisco. But companies like Hewlett-Packard Enterprise, for example, are setting up a whole supply chain to supply silicon photonic technology. Also, some companies are more into fabless, fablight mode, but also are proposing technology based on silicon photonics for integration or interposer. System, JePPIX has announced a transceiver based on silicon photonics, and at the end, also big company, big GAFAM, Google, Microsoft, Facebook, they are the company driving the need for new technology, new photonic technology to lower the cost, higher data rate, as are a big driver to develop new photonic technology, new silicon photonics. Interesting to see that there are some integration, vertical integration in photonics. For example, the acquisition of Cisco with Livewire, it was in 2011, I think, was the first Livewire, was the first silicon photonic technology company acquired by Cisco. But after that, they have acquired Luxtera and Acacia. Another example is JePPIX with Orion, or even I think this year was in February, was Nokia acquiring Elenion. And also on the other end, you have a GAFAM promoting some standard, trying to be more open, promoting open standard. For example, Microsoft, Facebook, setting up some standardizations for co-package. So there's a buoyant infrastructure, environmental, that will drive exciting development for photonics, especially silicon photonics. So we are market forecast company. So these are some market figure. So interesting to see on this graph, aggregate data from many reports, not only Datacom Telecom, but you can see that the highest data rate, growth rate is for optical transceiver and silicon photonic.
We need to hurry up a little bit, and I think on this slide we could stay for hours. So could you tell us what is the key message that we get from here? Because we could be hours talking about this. Okay. Just on this slide, just what you can see is that in terms of growth rate, silicon photonics will grow at 31%. So it's really the photonic technology with the highest growth rate among the others. And now quantum. We want to know about quantum. Yeah. Tell us. So quantum, just wait my last slide. So it is the next step after photonic-based sensor, photonics for communication. Really convinced that quantum photonic will be the next step.
First, because there is an increasing demand bandwidth and big data. So there's been an acceleration of quantum computer development. If you can see over the 2 past years, the number of announcements of quantum computer, the number of qubits handled by quantum computer have been increasing. And probably you know that there are different qubit technology for quantum computer. Superconducting is one technology, but because we are a photonic community, I will say that I'm really confident that photonic-based qubit, which is the equivalent of bit in quantum world, could be a technology for the future of quantum technology. Because of 2 reasons. It can be operated at room temperature, which is a big advantage compared to superconducting qubit. And the second strong point, you can leverage semiconductor technology. For example, you can see on the graph, on the picture, on top right, how by using silicon photonic, you can miniaturize very complex experimental setup.
It is quite amazing what we can do with interactive photonics. Miniaturizing these setups, I know this one is from the Ludwig Maximilian University. Actually went to visit. It's from optical clocks all the way to interactive photonics, and that's really the goal. I'm getting a lot of messages from people in my WhatsApp congratulating you, especially on the slide in which you talk about price ranges. I must say that you have to be knowledgeable and brave to do something like this, and it's quite impressive. Are people going to get a copy of these slides? Can you distribute this?
Yeah, sure.
So anybody who wants a copy of this slide, send me an email or send Eric an email, and we will be more than happy to share them with you. They are truly priceless. One quick question, according to you, is there a market for indium phosphide integrated technology? And he points out, according to you.
Yeah, I think so. I have to say that we have not to make a competition between ENP and silicon photonics. They are complementary technology first, because silicon photonics will need INP for laser. And in some case, for integrated INP chips, there are already existing market for medical devices, and there are foundry in Europe already shipping integrated INP devices for very specific applications. So it's not as cost effective as could be silicon photonics, but for high performing and application where you need a lot of integration with different functionality to be integrated, yes, I believe there is some market for INP integrated technology.
I do agree with what Kevin said before you about the cost effectiveness being product dependent, and that's something that we need to be understanding. Mark has a question. He's from the panel, so he can ask the question himself.
Yes. Well, first of all, I hate the idea of indium phosphide being confused with silicon photonics. Indium phosphide is far superior. But my question to the gentleman is he aware of any silicon photonics companies actually making money right now?
Silicon photonics. Yeah. Intel is growing at more than 50% a year. Probably this year they will ship more than 2 million silicon photonic transceiver. As Cisco, etc., probably it will be around 4 to 5 million optical transceiver based on silicon photonics. I don't have the figure in mind, I can check, but I was really impressed by the growing number of units of silicon photonic based transceiver over the past year.
We have another question in the chat. Is from Michela let me say the name properly. Michela Svaluto, and she's wondering, in your vision, which is the envision expected road ahead for close to commercial quantum photonics?
Actually, there are already products based on quantum photonics. There are some high-end sensor, gravimeter, and atomic clock, which has this size, I would say, like a big shoebox, using quantum photonics. So it's not integrated photonics, but already product. Then the road to a quantum computer will be very long. I would say.
Yesterday, we had a meeting at EPIC on new product releases, and Quix presented their first 12-mode quantum computer on chip already as a product. And QSide last year they had already the quantum random number generator already packaged as a chip for photonic integrated circuits. Already 2 products in the quantum technology. Super exciting about this. Eric, you are fantastic, and your slides are priceless. Thank you so much for this. We move to the next presenter. We go to Germany. We get serious. We go to Hubert Suner, Cube Optics. And my good friend Sven Kruger has something to tell us about low-cost packaging for multi-wavelength solutions. Thank you very much, Sven, for being with us today. Tell us how we can help Hubert Suner being greater than already is. The floor is yours.
Thank you, Jose, for the introduction. And yes, we'll try to make optics great again out of Mainz, which is hopefully not only known for anti-COVID vaccines, but it's also a great place for optics. Yeah, let me talk about low-cost packaging for high-performance multi-lambda ROSAs and TOSAs. We already talked a lot today about co-packaged optics, and maybe before that we'll have chip-on-board technology. So let's go back in history, or let's look on the traditional approaches. So here you see just as an example, a typical 100 gig QSFP28 transceiver. So it has these type of gold boxes inside, so ROSA and a TOSA in a literally golden box. And so here you see the version from Cube Optics, but in general, they all contain the same. So you have an optical input or output, depending if it's ROSA or TOSA. And then inside schematically, you got if it's an LR or ER optics, so multi-lambda is for the higher speed is very common. It's not all parallel. So then you would have a demultiplexer cascade or a multiplexer cascade. In this case, it's based on thin film filters, and you got a focusing or collimating optics. And then as a ROSA, you have the photodiodes and TIAs, and then you got the electrical flex foil output. So all of that is contained in this golden hermetic box. Now, since some time, there's this tremendous cost pressure from these hyperscalers, from the Googles and so on. So their tremendous cost pressure is demanding for getting rid of these golden boxes. So to go to a non-hermetic or a simpler, lower cost solution, which would mean that photodetectors or lasers and so on are just mounted on the PCB transceiver board like a CDR chip already. And so this chip on board technology. But then you as well need some optical elements that take these beams from the lasers or put them on the photodetectors and go through a multiplexer cascade, and in a non-hermetic way, so in a very simple and low-cost approach. So it requires a non-hermetic open package to enable this ultra-low-cost coupling element of the PCB. And what we developed is what we call a WCM. So it's a WDM coupling module, very short name. So it's an ultra compact multiplexer for an easy and direct coupling onto these chip on board assemblies of the PDs and LDs, as well as you can use it as well in co-packaged optics, which would then be the next step afterwards. So it looks like this. It can host 2 to 8 channels. It's very flexible in terms of the wavelength grids. It can be CWM, LAN WDM, SWDM. You can have the TX and RX or TX or RX. As said, it supports coupling from lasers into the fiber versus from the fiber on the PDs, and everyone has his own. On the PCB, they got their own grids depending on the technology. So it accommodates from 250 to 750 micron grids for these PD LD arrays. Works single or multi-mode. It's compatible to coupling into silicon photonics, as we talked today, which is often a big issue. Not the silicon photonics, but how to get into the fiber. And as well, working with not only chip on board, but CPO co-packaged optics. So it's a very low cost design. It enables a very low cost plug and play type of assembly. So in a pick and place way you can assemble it to the PCB board. It has a very high packaging density. It's very small. You can put them side by side. Very interesting for CPOs. And in contrast to other technologies, it even has a very high performance because it's not based on AWGs. It's based on thin film filters. So they inherently give a very low insertion loss, low PDL, but a high isolation and a high return loss. And due to this non-AWG technology, it's a really perfect Gaussian beam shape. So it has a real single mode beam characteristic, and then it enables a high performance coupling of FR or LR, ER optics, 200 gig, 400 gig. It's not something fancy, futuristic. It's already in use at several Asian manufacturers. So to go back to that first picture, so this is now the coupling module. So these are all in scale to each other. So you see a rough comparison in size. It's some millimeters. And just to go back on the function, in here so it hosts that multiplexing function and the optical focusing or collimating optics, but it does not host this part, which is now on the board. So that would look like this. So you have that green thing here. That's the PCB board of the transceiver hosting CDRs and all the electronics. And as well, in this case, chip on board, it has the photodiodes or laser diodes on that board directly mounted. And so on top, you put that. It's roughly 4 by 4 centimeters and 2 centimeters high. And you can couple it to lasers or photodiodes, etc. And so it's just to show you the dimensions. So inside, we would have, so this is if you take up that housing, the housing is open, as you also can see here. It's just a metal cap to be able to grab it and to put it on your board. And inside you got a block. It's a glass block with the thin film filters. The red is the beam pass. And so this green thing is the collimating part. It's our polymer optical bench. So it's made by injection molding with an extreme precision. And so this is obviously the fiber. So let's say it's the input fiber. So that would be, for instance, a ROSA. So it would carry in this fiber 4 lambdas, for example, and it's attached to that block. And then it's a free space setup. So the beam bounces through these filters and the collimators and is then focused downwards to these photodiodes. And here you got the TIAs and so on. Same manner would be if it's laser diodes. And so then it will couple them, or first multiplex it and then couple it into the output fiber. This is already, as said, in production. It's also not, it's new, but it's based on proven technology. So actually more or less the same, the identical technology, but a similar setup is anyway present already in the 100G based CFPs, and several hundreds of thousands used inside those. So it's a very mature technology, and despite of being completely open, also a stable photocardia, which is of course of importance. Of course, if the transceiver itself is also not hermetic. So if you put it in a very dusty environment, then of course you'll have issues with this open approach as dust gets on the optics. Well, I would be very happy to have any questions, and hope you find more interest in that. Thank you.
Thank you very much, Sven, for another great presentation, and thank you for bringing the low cost technologies to what photonics needs to be in the short-term future. It is, of course, the room is open for questions. This is very interesting packaging technology. I'm going to ask you the epic question: what can the other members do for Hubert's Cube Optics, and what can you do for them?
Well, we'd be very happy to work with the guys in the silicon photonics area, and so addressing any issues they might have in coupling.
Very good. You presented very interesting packaging technology today, and you claim that it's low cost. Could you comment if it's suitable for passive or active alignment?
Yes, it's so it's very suitable for passive alignment. So there are actually some marks, visual marks, and so with cameras you can see the position or you grab the part, you see the visual mask in your camera system, and you align it to the PCB in a standard alignment, passive alignment process.
Thank you very much for that. And of course, if there is any room for cooperation or question, we want to hear it. In the coming next two presentations, we're going to hear about micro optics for the packaging of optoelectronic devices, and there's obviously room for cooperation that you need to interact with. Thank you very much, Sven. Let's continue with the program. And now you must know something, that is that Europe is really living the revolution of micro optics now. We have companies that are growing dramatically because they managed to master wafer level production of micro optics, almost free forms in pilot and volume production, going to semiconductor, but also going to the consumer market, like in the mobile phones and the automotive. Let's see what we can do for telecoms. Wilfred Noll is here with one of the success stories of this ecosystem with SUS Micro Optics. Tell us about SUS Micro Optics and what can we do for the packaging of photonic integrated circuits and other electronic devices. The floor is yours.
Thank you, Jose, for the invitation, and I'm very honored to be part of your TechWatch today. I hope you can hear me well.
Loud and clear.
Thank you. So the last few talks were very good. They really showed it's all about volume and packaging. That means we used to just sell micro lenses and said, okay, and you take care of the packaging. But this is not the case anymore. We really have to go to the next level and offer more packaging features in our micro optics. So we are a micro technology fab in Switzerland, in Neuchâtel. We're around since over 20 years now. We make refractive and diffractive micro optics. We have a clean room now, and as Jose said, we're just building a new clean room dedicated for automotive optics. This is polymer-based optics, so it's not like injection molded, but what we call polymer on glass. So this is for very high volumes and very low cost. I have to say, we do in one day, we do the same amount of lenses for automotive that we do in a year for telecom. That means, so the volumes are very, very different. Huh? So, I mean, we make hundreds of wafers for automotive in a week, and for telecom, it's also a large volume, but the number of lenses it's just orders of magnitude different for telecom. Telecom is about packaging, so you have to be extremely accurate, and you have to be also very reliable, especially when we look at what Sven just showed. It has to be very small, it has to be very reliable. So which polymer optics are very reliable, but polymers are not there yet to deliver to the datacom market, in my point of view. That's why fused silicon-based optics are still very strong. So we are very active there, of course. We've been in the market for over 20 years. We started off with beam shaping optics, and now a large portion of our business is, of course, fiber-based optics or waveguide optics. PIXAPP are very strong. The question before came from if anybody makes money with PIXAPP in transceivers. This is a good question. We see that the market is huge. So the majority of our customers, they use PIC in their business, but I don't know if they make actually money. This is a different question, but definitely the market is very, very strongly going in this direction. And that's why we're still offering a large variety of products. So we offer here these very simple lenses. So what I have here on the left side is a form factor of the lens, going from what we call protruding lenses and recessed lenses to lenses with a lot of extra features for packaging. And on the right side, you see some typical applications. And so on the right side, you see the packaging becomes easier when you go down, but the costs go a little bit up. So the cost factor between a simple lens and a lens with these features, there's it's not much of a difference, but it's a very price sensitive market. So that's why the middle lens that you see here, this is about the sweet spot where packaging becomes very easy, like with these prisms, and the costs are still very, very reasonable. I can't give a cost overview like Joel just did. Of course, I'm not allowed to do that. So these simple lenses, so it's always interesting to see there's few silica silicon. So silicon, because of its high refractive index, can be very, very flat lenses, very cost-efficient lenses. Whereas few silica, it's very easy to connect to fiber. And you can have these large beams here. So that means it's very good for very large coupling distances. You can't do the same with silicon, but you'll have to let the light first propagate outside the silicon in order to get the same beam diameter. So that means silicon is great for very flat, very inexpensive lenses. Whereas fused silica, it's a very, very compact solution. And so we actually sell both to the datacom and telecom market. We really don't really mind doing either one. Sven just gave a very nice introduction to TWM4s. Don't have to dwell on this too much. We do a lot of optics there for the collimation side here on the left before the glass block and the filters. And we also offer these lenses on the right side that couple directly onto the either the photodiode array or the laser array. So we can do that in singlets, or we can do that with an array shape, of course. Like I said before, this is the what is very popular, these microprisms on top of the recessed lenses. So you see how this can be mounted directly onto the lens. And there's a shift in here. Fix that quickly. So that means the microprisms are directly on top, mounted on top of these recessed lenses. We can make glue pockets here. It's very quickly combined with a fiber or PIC or VCSEL. So VCSELs are actually coming quite strongly at 850. There's more and more business going in that direction. So I'm pretty sure that 850 will grow beyond short reach soon. We're waiting for this. This is very interesting to see. Of course, grading couplers are the bread and butter for PICs. And so we offer all these types of glue stops. And then there's a nice air gap in the back. So when you have a very compact silicon lens, the beam diameter that you get here for collimating is very small. So you need a little bit of a combination of an air gap and a silicon thickness in order to get enough beam diameter here on this side. Otherwise, you can use a fused silica lens. That's the other option. And then, but then it's the whole package is different. And so again, fused silica or silicon both works in these arrangements. What we also offer now is we're working on very strong in this. We're continuing to do this. We have identified this as a strategic project. We're investing more people and money into this now. Is integrated prisms into the silicon. So that means we have a microlens here that is right below a prism that is integrated into a silicon wafer. That means you can have directly 90 degrees turn. And we also have a technology to make a nice flat surface here on the right side. So you can directly couple either a PIC or a fiber to this side. And here then you have either collimated light at the bottom, or you can go directly into another optical element. So that means we do the whole design here. We can help you with the design. We can think about features that help you packaging easier, and it's very compact design. So if you want to have it even more compact, then there's a last solution that I hope show here. These are Fresnel lenses. It's extremely flat. We're selling these a lot now for low NA. It's like a fiber, an optical fiber at 1550 or 1310 is a low NA optic. So this can be enough to couple light or collimate light over short distance. So that means, but it's extremely flat, extremely compact. And why is a Fresnel lens better than a round lens? You can do any form factor you want. You can make it elliptical, you can make it circular, you can make partial lenses. You can have the lens being off axis. So you have a lot of options with a Fresnel lens that you don't easily have even with grayscale or reflow based lenses. And this is how I like to finish. And we are automotive certified. Thank you, Jose, for mentioning this in the beginning. So we are fully automated, certified for automotive. That means applications like LiDAR or headlamps or other outside lighting, exterior lighting or interior lighting for automotive. We can do all of this now. We're doing this all now. And for that, you need the automotive certification. And we are fully certified in this way. Thank you for your time.
Thank you very much, Wilfred. I can't stress enough how important it is for the current European ecosystem, the growth of companies like SUS Micro-Optics, like Axetris, like Nanoscribe. The whole idea is that we can now do multi-level micro-optics at very low cost thanks to the very optimized replication process. We have a question for you from Mark.
Hi, Mark.
Yes, on the VCSELs, you were impressed with the growth level. The 850 nanometer VCSELs typically grow about 10% per year. Are you suggesting it could be higher than that, or would you know about that?
That's a very good question. I like to have that answer too. So, but what we see more and more people, more and more clients asking for 850. So, and the VCSELs are very nice. They're getting more and more stable. There's this, Jose, remind me of the name. There's this company, I think they're in Berlin. They offer now VCSELs in for data and telecom datacom applications with very high data rate, and it's becoming very impressive.
VI systems. VI systems. VI systems.
VI systems, exactly. So VIS, yeah. So this, I mean, this is coming. So VCSELs are coming. Of course, VCSELs always have this reputation about reliability with large temperature ranges. This is why they have some trouble in some markets. But here, I mean, they're already there for short reach. They're already out there. There have been proven reliability. But the actual growth rate, I like to know too, Mark. That's a good question. Huh? But I see more and more requests in this domain. So.
Charles Goller is asking, I was just wondering what is the minimum size reachable for these micro-optics?
So the smallest micro lenses we do are 20 microns in diameter. So, and actually when you go to other technologies, you can go to a few microns. So, but our what we call standard size is like 20 to 30 microns. This is we have done. We're just running a 2-3 projects these days with these small micro lenses. This is usually for very different applications, not data telecom, because the beam diameter is very small. In datacom, we've been doing typically 250 to 500 micron lenses or lens pitches, whereas in telecom, the pitch has been 127 microns since decades. So we've been doing 127 micron pitch since over 10 years, and but datacom is not there yet for whatever reason. Typically, the coupling lengths are longer, so they need larger beams. But so, and also we do 80 microns is also one of our standard sizes. So we also do 80 microns. So
Wilfred, I want to combine your presentation with the next one because afterwards I want to address the topic of co-packaged optics, the elephant in the room. Axetris is here to talk to us also about micro-optics. Myung-Sik Kim, thank you very much for being with us on this fantastic TechWatch. Tell us about Axetris and how we can help you revolutionizing the micro-optics manufacturing. The floor and the attention of everyone continues in Switzerland and goes to Axetris. The floor is yours.
Thank you, Jose, for introduction. Yeah, this is Magic from Axetris. As you heard, Axetris is a leading manufacturer of micro-optics, including micro-lenses, micro-lens arrays, and diffractive optical elements as well, like SUS does. But that's typically what you hear and what you learn about Axetris. But in fact, we can do a lot more than that. So today I will talk about what we can do more than micro-lenses. So this is my agenda. So I will briefly overview our mother company, Leicester Group, and Axetris business activities. And then later I will focus on our micro-optics and service, where we can provide you MEMS foundry fabrication services, and also micro-optical elements. And then my main topic, further capabilities, add-on features, what we can do more on our micro-optics. And those further capabilities, in fact, what was not developed only for micro-optics. That was we learned and drilled the fabrication technology for our sensor business unit. So I will briefly introduce as well about that. So this is Leicester Group business activity. Maybe you're not familiar with Leicester, but Leicester is very famous for the plastic welding, process heat, and laser plastic welding as well. And these days, these industrial tools becoming smaller, like handful size, and this is for the do-it-yourself. And Leicester Group was founded in 1949 in Germany, in Solingen. And then it started to move to the production headquarters to 70s, to the Switzerland, where we are now located, and close to Lucerne area. And then Leicester started the high-tech diversification project about 22 years ago, 1998. The same year, I think, as the SUS Foundation. At that time, very sweet spot in the high-tech was microfabrication and microtechnology. So we catch up this idea and building up the microfabrication technologies and MEMS sensing devices along with our micro lenses shown here. So after 22 years, we are now 150 people. Our core competencies are micro optics and sensors. We have a production infrastructure larger than 1,000 square meters of clean room. We can operate from 4 to 8-inch MEMS processes, front and back end, and assembly and test. We also have a qualification system ISO 9001, and we have, in fact, not only the micro optics, but as shown in the right side here, we have 4 product lines. One is I'm belonging to micro optics, and the other is infrared source and mass flow devices. We combine them as a sensor business unit. So this is our world market presence. In fact, our headquarters production is in Switzerland, but to the east, we have a sales offices in China, in Shanghai, in Shenzhen, also one in Japan, in Tokyo, Shin-Yokohama area, and 2 offices in US as well. One in Itasca, Illinois, in the close to the East Coast, and the one in West Coast, South Bay in Fremont. And all the sales offices has our local sales managers, so we can serve you worldwide any inquiries. As I said, we start to build our fabrication technology as a MEMS foundry, and we start to offer fabrication services. What you do is wafer level manufacturing services. Some of them is shown here on the right side. There's some pictures. So we can operate from 4 to 8-inch wafer processes, and we can do thin, thick photoresist lithography and structuring and etching silicon glass substrate, and also some special metals. And special metals are, we can structure metallization, multiple levels of different metals and sputterings, accordingly metrology and characterizations. In fact, our MEMS foundry offers non-standard process, which means some of the standard foundry services, they do not want to have a special metallizations in order to avoid cross-contaminations. We can offer, and we can do typically as well as shown here, like post-CMOS processing, which means we can structure or we can do the metal patternings on top of wafers which has a CMOS or sensing devices already. And with this fabrication technology, maybe you can imagine how we make micro lenses. So typically front end, we can do the patterning with UV lithography with the photoresist coating and exposure with a shadow mask. And patterned polymer can be reflowed with thermally and becoming spherical shape. This is already kind of a lens, but nobody wants to use this lens as a product because of this is polymer and substrated hard material. You will have aberration at the same time reliability problem. So we need to transfer this one to substrate by plasma etching, as you can show here. But typically after the melting, this is spherical lens. And we can tune sphericity or asphericity by tuning the selectivity from the polymer to the substrate. We can make a spherical lens. So we end up with a full of lenses on the wafer. We do the AR coating, dicing, and 100% visual inspection, and do the pick and place packaging. Packaging as well, depends on your need, small number of chips on the gel pack, on the tape, etc. So this is how we make micro lenses. With this technology, we can offer to you, to our clients, micro optics, including reflective lenses and diffractive optics. Shown some examples are shown here, reflective lenses. And so we do as well the DOE and gratings. So applications are, so today's topic is more about the transceiver and datacom and telecom. It's shown here simple schematics of the TOSA and LOSA, laser diode coupling to the fiber, coming to the ROSA, which is coming to from the fiber to the detectors. So our lenses are mainly used for the transceiver optics in TOSA, ROSA in the datacom, and in telecom as well, transceivers or more advanced modules like wavelength selective switches as well. And some other applications are DOEs or gratings can be used in industrial beam shaping, beam splitting, or homogenization applications. As well, some of our product goes to the automotive or consumer, especially the IR sensing, 3D cameras, and lidars. So this is we are offering to you. Here is some examples of our micro lens product. So we can make even the lenses like generically patterned, like lenses everywhere. We can dice as you want, like big MLAs or single lens chips or multiple lens chips like 1x4 arrays, 1x10 arrays, different sizes. As well, we can design, manufacture as your customized designs like single lens chips typically used in the TOSA and LOSA single lens. Not only we can do the circular lenses, but also we can do cylindrical lens arrays, cylindrical lenses as shown here. Like this is typical slow axis collimators and fast axis collimator used in the WSS, the wavelength selective switches. And as well, this is shown for here is a typical beam generator by cylindrical lens arrays or beam homogenizers. Up to here, you know a lot about us, but we can do a lot more than that, as I said, further capabilities. So metallization, for example, chromium, tantalum, aluminum, tungsten, tight tungsten, gold, platinum, gold, tin. All this, in fact, metallization, we can do multiple or different metals on top of our chips by our capabilities. Some of them is on the shown on the right side, alignment marks or alignment structure. Some of them is light blocking. Some of them is mirror. Some of them, for instance, this one is soldering pads. High temperature, the reflow soldering is possible with our lens chips as well. And the mechanical features, SUS Microoptics showed a lot about mechanical features like backside cavities for the glue resolver or optical spacing, or as well the DBAR for the very precise definition of the chip. And here as well glue stops, etc. And we can do the front and back side processing, double-sided lenses, alignment marks, as well recessed lens shown here, soldering pads, and backside cavity, wafer bonding as well. In fact, all these things where we can use, if you think about simple transceiver here, you don't need all these things. You just maybe a few of the glue stuffs like this. But if you talk about, if you just recall the presentation from the Uber and Zuner or Wilfried, now it gets assembly and packaging gets more complex. And they have a much less space. On top, if you want to combine with active devices like detectors or lasers, you need to have electrical connectivity as well. So you need some metal patterns or metal circuits on your micro lens chips. That's how we can offer from prototyping to the mass production. Here, the mass production I want to specify, we can deliver to you as you want, whatever features, whatever micro lenses, from a few hundreds of pieces to some millions per month. If you want to have some millions per week, probably we can do as well in near future. So this is what we can do for you in micro optics. But as I said, all these capabilities were not developed for micro optics. In fact, when we started, we had like MEMS sensor devices. Here is a few examples are shown, especially these two infrared source and mass flow devices. We need to manufacture active MEMS devices. For instance, this is the infrared source made on the silicon membrane with special metal patterns and as well depositing high emissivity layers. So shows the picture is here. So this is a active MEMS infrared source. And then this is a mass flow device, which is shown the picture. In fact, this is as well complex MEMS, active MEMS sensing devices combined with a heater, with the temperature sensors. If you can measure the temperature gradient from the entrance to the out, you can get the mass flow. So by manufacturing these all complex active MEMS devices, we gained a lot of capability for structuring substrate and as well multiple layers of different metals, connectivities. So we are expert in additional features as well, not only on the micro lens manufacturing. This is in fact all I want to say. And then if you have any questions, thank you.
Thank you very much, Music Kim, for this great presentation. Thank you for being part of this incredible TechWatch that we are living today. For me, one of the elephants in the room is the topic of co-packaged optics. So there's been in the last 2 days lots of presentations from top companies about co-packaged optics. We have the optics manufacturers, the micro optics manufacturers with track record on the telecom datacom market. Do you know what this industry needs from you, and do you have a roadmap to deploy, to manufacture it for them?
Thank you, Jose, for the question. Yes, in fact,
Excellent
we are
question.
working currently with the the core package or like a Kobo core package or further like micro integration companies. So some of them, they need, in fact, connectivity to their active devices. So they need to have like not only the, for example, soldering or not only the blocking metal layers, but also the electrical connection like metal circuits. So that's one kind. Then the other is, if you want to have as well the firm and miniaturization packages, sometimes like shown here, do you see still my screen? Like you need the soldering. Soldering needs special metals for high temperature. So your chip need to survive over, for example, 300 degrees for several tens of seconds. So then need as well the additional reliability for the your material itself and some other air coatings, etc. So we are working with those clients, and so I just said two main features, maybe soldering and electrical connectivities. But there are a lot more requirements, but we try to solve them with our clients. Yes.
I love this slide in your presentation. Let me share my screen. I love this slide in your presentation in which you showed different metallization processes for
Yes.
micro optics. What is the common request that you get from this industry and which metals to use for coatings?
So the soldering is maybe this is not a big secret, so I can tell you. So soldering is typically use the tin, but gold tin is the preferable choices. And then electrical connections depends on your circuit, so I cannot tell specific, but soldering is a gold tin. And sometimes as well the blocking layers for in the like shown on the right side, blocking layers or indications can be done with chromium, the cheapest way. But majority of done can be gold for the high quality and reliabilities. And sometimes you need the high reflectivity, then you need to use as well other kind of like platinum or aluminum mirrors.
When it comes to reliability, that's an important question for me. What is the process? Do you just go through the Telcordia standards, or is there any other thing that you need to actually qualify this?
Exactly. So our standard reliability is a Telcordia for the communication business, like telecom and datacom. On top, if there is a soldering processes, we do additional test for the high temperature endurance test. Yes,
as I promised,
depends on soldering process. Sometimes over 300, could be 250, but usually over 300. Yes.
As I promised in the previous Q&A, I want to go back to SUS Micro-Optics because I want to ask him the same question. The elephant in the room is co-package optics. There are different views. We were very happy to hear Mark's views, but there also been other presentations yesterday and the day before. Do you get from this industry what they want in the field of wafer level micro-optics?
This is a very good question. So co-package optics. So the thing with co-package optics is what we see. Of course, we're working on this. Just like Munzik just said, of course, we are all working on co-package optics. We work with all the big companies on this, but it's a different mentality. Companies who come from co-package optics, these are typically packaging people. These are companies who are used to assemble electronics. They want their metal interfaces. So we offer also these gold tin metal pads. We offer this also. We do that already in high volume as well. But the mentality is a little bit different. Extremely low cost, very high volume, high temperature stability, and very large areas of micro lenses. This is where co-package optics are going, and we're actively working on this. We're helping our clients with the optical design there, because then, like I said, these aren't usually not optics people. These are electronics and packaging specialists, and but it's coming. But it took a while to speak the same language. So this is our learning curve on both sides. So but it's coming. It will be there. And we are ready. So
it's a huge market, and they want what we have. They want large area. We do wafer level. They want high resolution. We actually are doing free forms now, and they want high reliability and low cost. We have replication technologies for that. So this is a huge market for us. Thank you, Wilfred. Thank you, Muson, for this. Axetris and SUS are just examples. A huge push for micro optics in Europe. Thank you so much for revolutionizing the industry. And we go now to one of the most beautiful stories I have heard in the VCSELs for Datacom in the last years. Politecnico di Milano led a European initiative called Passion, in which they wanted to take the VCSELs from Vertilas and put them all the way to metropolitan area networks in terabit per second links. Let's see how they did it and how we can help them doing even better. The floor and the attention of everyone goes to a rock star, goes to Professor Pierpaolo Boffi. The floor is yours.
Hi, Jose. Good morning to everybody. So as Jose said, I would like to present the innovative technological solutions enabling multi-terabit transmission developed during the PASSION project.
Pierpaolo, we still cannot see. No, it's here. Yes, the floor is yours.
PASSION is a European Horizon 2020 project started about 3 years ago, coordinated by Politecnico di Milano. And you see the partners, including in the teams, not only coming from Europe, but also from Japan, from Korea. So the aim of the project is to design and develop an innovative sliceable bandwidth bitrate variable transceiver, SBVT, sustainable in terms of cost, power consumption, and footprint, and assuring multi-terabit transmission. So to reach this target, first of all, we employ low cost and energy efficient sources such as VCSELs in indium phosphide emitting in the C-band and with a high bandwidth, and the VCSELs are modulated not externally, of course, but directly with multi-level formats such as PAM4 or better DMT. DMT, thanks to power and bit loading, allows to match the not uniform and bandwidth limited response of the whole communication system, and in this way can increase the transmitted rate. And in this way, we achieve at least 50 gigabit per second per VCSEL, also starting with a limited electrical modulation spectrum below 20 gigahertz. And then we exploit also WDM with 30 VCSELs covering the C-band with 100 gigahertz in spacing. And finally, the developed SBVT is implemented in a silicon photonics platform with massive integration, integrating the 30 VCSELs all together in the same SOI chip in order to realize a single module with an aggregate capacity up to 2 terabit per second. So you can see here on the left, the concept of this 2 terabit per second module constituted by this SOI chip embedding 40 VCSELs, their drivers, and the lambda multiplexer. In particular, we put 10 indium phosphide VCSELs on each side. The VCSELs are produced by a German company, Vertilas, and they are characterized by single mode operation in the C-band with a target bandwidth of 20 gigahertz. And we demonstrated the possibility to achieve beyond 50 gigabit per second per VCSEL with a power consumption lower than 30 milliwatt thanks to DMT modulation. And you can see here the design of this silicon photonics chip realized by the Finnish research group VTT. In the middle, there's the AWG multiplexing the 30 VCSEL emissions into a single output waveguide. And you can see the realized chip, and on the right, the picture of the electrical interposer with the photonic chip in the middle and the VCSELs all around. The dimension of this photonic chip is 2 centimeter by 2 centimeter for a corresponding capacity of 2 terabit per second. And the power consumption of this optical chip is around 5 picojoule per bit. You can see here also the assembly of the module and the final transmitter board realized by the Italian vendor SM Optics. So these 30 VCSELs module constitutes the passion fundamental building block in order to provide multi-terabit transmission. And in particular, we adopt a modular approach. What means modular? That we fabricate identical modules, such as the described one, in order to realize a more complex super module with increased capacity. In particular, the 30 emitted wavelengths from the VCSELs can be tuned all together in the same module in a range from 0 to 75 gigahertz. And in this way, by combining 4 of such a module, it's possible to aggregate 160 WDM channels with a lambda granularity of 25 gigahertz in order to realize this super module with a total capacity of 8 terabit per second. So, of course, we can exploit also polarization division multiplexing by combining the outputs of 2 identical super modules orthogonal in polarization, and in this way we achieve 16 terabit per second capacity. And spatial multiplexing can be also exploited with bundles of fiber and multi-course fibers. And in this way, we can achieve also more than 100 terabit per second per link. That is the target of the project. So coherent detection can support these very, very challenging applications, not only to manage the polarization, but also to compensate the chromatic dispersion. Let's consider that we employ direct modulation of an intensity modulated DMT. So this means that we need a very simplified version of coherent detection, so without frequency and phase recovery. And in this way, we can reduce the complexity of the DSP at the receiver side and to relax the constraint related to the line weight of the local oscillator and of the VCSEL, of course. So we are experimenting this 2 terabit per second module in our test bed in Politecnico di Milano and in adrenaline test bed in CTTC lab in Catalonia. This test bed is equipped also with network nodes, multi-core fibers, and so on. And you can find preliminary results regarding the performance of this system in last OFC and also in a paper to be published in a special issue in JOCN in the next. So I've shown you the innovative technologies proposed by Passion in order to enable multi-terabit transmission in a sustainable way in terms of cost, footprint, and energy consumption. Of course, the application considered in Passion is the metro network, but the same approach can be applied to other short and medium reach applications. Regarding what can we do for you and what can you do for us? So we are open to collaboration, of course, to test our technologies in other test beds, in other field trials in order to check the effectiveness of our solutions in different applications, and on the other side to check your components and devices in our test bed in order to understand the synergy with other other technologies in our solution, in our approach. Thank you very much for your attention.
Thank you very much, Paolo, and congratulations on what you have achieved, because it is not easy to speak the language of VCSEL manufacturers and speak the languages of Telefonica as a telecom service supplier. And you managed to bring all of them on the same table and managed to bring a big bridge between high-speed VCSEL-based transceivers and service suppliers. One question here. Ideally, you first define the whole optical network for metropolitan area networks. And lately, we have 5G already here. 5G is here. 5G is just the beginning. We just is tip of the iceberg on new capacity developments for optical networks. Did you have to define the optical design, the optical network design, or are you adapting what you are doing for this 5G world?
Yes, of course. So the passion approach can be applied also to other applications. So, for example, now we are analyzing the metro network. In particular, we are considering the needs of a big city such as Mexico City, with an impressive number of users, traffic, significant distances between the nodes and so on. But of course, you can apply the same approach, for example, for the 5G XHAul, fronthaul, backhaul, and so on, when you need also a huge capacity. And now we are considering the C-band, but of course, you can use also other bands. For example, we can exploit O-band. VCSELs in the O-band are available, and so we can also redesign the SBBT for other application, tailored for this type of application with huge capacity.
Mark is a huge fan of VCSELs for telecom, so I'm not surprised he has a question. What's on your mind, Mark?
Well, he mentioned the O-band in his slide just now. I'm just wondering where he's seeing the applications for it. I mean, we see some L-band for submarine, but I'm not sure where the app is for the O-band. Where are you seeing it, sir?
So of course we can exploit also other bands, of course. O-band, because at the moment the VCSELs are available in this range, but for example, also other bands can be considered for different applications. Of course, and now we consider that we are exploiting VCSELs, but we can exploit also other kinds of sources. For example, DML with the same approach, but of course, in this case, the massive integration is obtained with the VCSELs.
Selena Liu is actually telling us in the chat that she has C-band. Please, Selena, tell us what you have in mind, and we're more than happy to comment. Professor Pierpaolo Boffi, one thing that we want to now look at is to go to the next step, to do a deployment phase. What companies do we need on board to make this something real? So
first of all, operators, because of course we can check the performance in real field trials, and so now we have on board Telefonica, that is the principal partner to check the capabilities of this solution, and on the other side, of course, vendors, because for the realization, we have now the bird realized by SM Optics, but we are open also to consider the interest of other companies that can be interested in the development of a product, also for other applications, not the meter network, but also for other applications. For example, datacom, this is another possible field for inter-data center interconnections.
It is great that we have fantastic VCSEL technology in Europe. Stefano Prandoni from Bandwidth 10 is telling us about their C-band technologies. We have also VI systems. We mentioned before, you're working with Vertilas, a great VCSEL manufacturer. We are doing the wafer level testing on them. We are doing the micro optics, packaging them into systems. We are putting them into silicon photonics with PIXAPP. We have indium phosphide technology for integrated photonics. And we have a whole ecosystem with the low-cost packaging of Huber and Sooner, with the market knowledge of Joel, and with great comments from Mark Lutkowitz. I have a credibility for Mark. I cannot avoid it. Mark, that was great. Thank you very much, all of you, for another epic session. I would like to encourage all the attendees of this session to now go to the virtual booths of all these companies and have a discussion with these people, because they love talking about photonics half as much as I love talking about photonics. Until the next time, continue being epic, wash your hands and wear a mask. Take good care of each other. Bye-bye.
Bye-bye.
Thank you very much, everyone. That was a really nice session. I really enjoyed it. I'm going to give the floor, all the hosting rights back to the ECOC organizers, which means that I no longer have any power here. But thank you very much, the organizers of ECOC, for a great meeting. I really enjoyed it, and I already got some good comments in my WhatsApp and in my Skype from people that were listening. So that was really good. Thank you.
It was really good, Jose, huh? And a few new things that didn't show up in the last EPIC event. So that I like that very much, huh?
It's really nice when you have your friends around, then always the good things happen. You have Sven and Pier Paolo and Eric and Wilfred. It's really cool. I really enjoy this. And this afternoon we have a meeting on medical devices. I don't know if any of you are going to be there, but it's going to be.
I signed up for it. Yes, yeah.
With Medtronic, with GE Healthcare, so quite good
Sven's
stuff as well.
Talk was great. It was really good. So that was really where the road is going, huh? That's basically co-packaged optics. What you do at Cube Optics, huh, Sven?
Yeah,
it's close.
Yeah, it's the optics too. It's more chip on board usage now. So, but we have some projects where we're working on co-packaged optics. Yeah, although I somehow have to agree that co-packaged optics in reality are still probably a little bit far out, and they have a lot of disadvantages for the users, but this is not on us to decide. I mean, I like the technology.
Yes. So we see it too. Of course, we can't talk about it in detail, huh? But we see it too. These are very different people you deal with co-packaged optics. These are not the classical optics designer who have done 20 years in data or telecom. These are completely different people, and it takes a very long time until we speak the same language. It's not easy, huh? But it's challenging.
Yes, very true.
Yeah.
Yeah, I mean, the idea of co-packaged optics is so old, no? I mean, optics on, yeah. And it never, I mean, there was always announced, okay, now it's happening soon, so.
And again, 20 years talking about co-packaging. This is like, this is, you're right, Sven. I am always worried about making that point.
You know that Cube Optics and we was the same. We were working in the same group in Mainz. Huh? There was a spin-off of the same group. That's where I did my PhD. In that group, we were a group of 8-10 people doing micro optics there. You know, and or nano optics. I did nano optics. You guys did micro optics. You spun off, became successful. I spent 20 more years in academia. Okay, but this is So that means we have seen it all for a long time, huh? But it will be coming one way or another, huh? Yeah.
One way or another, or not at all, because Bye. You know, the first ECOC that I walk around and I don't see any of the package boxes from the Chinese companies that they are looking, that they look like. The first day that I don't see that, I will be a happy person. Still, there is this huge push from the Chinese companies on the low-cost transceivers, pluggables, and it's not there to live.
The cost pressure is dramatic now, huh?
So it
is. Datacom. And it starts now for telecom. The cost pressure in telecom was usually not as bad, but now with 5G, the cost pressure becomes even in telecom quite dramatic, huh?
Yeah, and I was listening to a market from light counting. So, and the number of transceivers used for front hauling doubled. So the market volume doubled from 18 to 19, but now it again has reached a maximum and is now declining again. And it's all because of China. Because of 5G rollout in China is almost, it's already over the peak, and the rest of the 5G deployments are so slow in the rest of the world. So
because
the
of
market
Trump.
is
Not sure.
All right. Well, I hope, you know what would be great if we could all now, the three of us, go for lunch. But we can't.
Yes.
So I have to leave, but it was great to see the
Okay.
two of you. And I hope until the next time, take care and see you soon in
Bye-bye.
Mainz and in
Yeah.
Neuchâtel. Bye-bye.
In the afternoon, there's the next session, no? Afternoon, the EPIC session, a preparation on your great conference, the Photonics show in
Yeah,
February.
we do so many things, but that's the Photonics Plus is more on Carlos' side. So this afternoon I do medical device manufacturing at 3 o'clock. Medical
Yeah.
device manufacturing. It's
I
going to be a
cannot
super
join
nice
both.
meeting
See
with
you later,
GE
Jose.
Healthcare and
Medical.
Medtronic. See you. Bye-bye.
Bye.